going to look today at some Year 12 trigonometry. A lot of it is GCSE, but just a few things to bear in mind. We've got a couple of intro things before I actually look at the examples that are on the sheet. So that's why I've labelled it as O1A and O2, because there's a sheet of printouts, some of which is to do with something called radians, which we'll see later on in the course. That's not for today. But a couple of things to look at initially. We've got two trig identities in this AS part of the course, and it comes from initially basic right angle triangle. We've got angle theta, base x, height y, and hypotenuse h. So I'm going to do the obvious things. I'm going to say what sine theta is in terms of my letters: opposite over hypotenuse, cos theta, adjacent over hypotenuse, and tan theta, which is opposite over adjacent. Now, if I take sine over cos, like this, I get y over h divided by x over h. If I cancel the h, or times top and bottom by h, that's exactly the same as y over x, which is tan theta. And there's my first identity. So I'll put it over here. Tan theta is sine over cos. And that's true not just in a right angle triangle, but for all values of theta. The second one I'm going to do is from Pythagoras theorem. Pythagoras theorem gives me x squared plus y squared equals h squared. And this is going to generate what is called a Pythagorean identity. There's actually three of them. We're only going to look at one of them in the AS course. If I divide every single one of those three terms by h squared, what I get is x over h all squared plus y over h all squared equals 1, and x over h is cos squared theta plus sine squared theta equals 1. We have this unusual way of writing powers of trig things with the power here, because if we wrote cos theta squared, it might get confused. If you wrote cos of 30 squared, someone's going to square 30 first and then press cos. So it's where your brackets would go. So to avoid it, we tend to write this notation here for squaring and cubing and so on. It's a little bit different when we've got 1 over cos, 1 over sine, and 1 over tan, but we'll cross that bridge another day. It's also handy, in particular for other parts of the course, particularly for things like mechanics, to look at standard angles. You're going to see a lot of 30s and 45s in particular in your diagrams that you're going to do for other parts of the course. So I'm going to look at three different triangles here, an equilateral one, all sides of 2. So I'm going to split it in half to get 1 and 1. Because it's equilateral, I've got a 60-degree angle there and a 30-degree there. Pythagoras tells me the height of the triangle is the root of 2 squared minus 1 squared, root 3. And then bit by bit, I can pick out sine 30, opposite over hypotenuse, half. And that's exactly the same as cos 60, because what's opposite one angle in a right angle triangle is the adjacent for the other one. So cos 60 is also half. Cos 30, adjacent over hypotenuse, root 3 over 2, which is the same then as sine 60, root 3 over 2. And tan 30, opposite over adjacent, 1 over root 3, which a bit of surge work is the same as root 3 over 3. Never like seeing surge on the bottom of the fraction. Similarly for tan 60, root 3 over 1 is simply root 3. This triangle here is an isosceles right angle triangle, so because it's equal sides, we've got two equal angles, both 45 degrees. Pythagoras tells me 1 squared plus 1 squared is 2, and square roots to get the hypotenuse is root 2. In this case, sine 45 and cos 45 are both the same, 1 over root 2, root 2 over 2. And tan 45, either way around, is opposite over adjacent, 1. When I'm looking at 0 and 90, I'm going to consider a very small angle and think what happens as that gets smaller and smaller and smaller. Opposite over hypotenuse, well, the opposite side gets smaller and smaller and smaller, and that will tend towards 0. And similarly, cos of 90 will be the same thing as before. Whereas when I'm looking at cos of the small angle, this side here and this side here are almost the same, and as this gets smaller and smaller and smaller, the two will get closer and closer to each other, so when I divide them I get 1. And that's the same as sine of 90. And similarly, if I did tan of the small angle, opposite over adjacent, that tends towards 0, so 0 divided by anything tends towards 0. But when I do this one here, the big angle, opposite over adjacent, as adjacent gets smaller and smaller and smaller, I'm basically going to divide by 0, so I'm going to tend towards infinity. So those are our sort of standard results that match up with your graphs that you've seen at GCSE. So we're going to look particularly, in slightly different order than the book, but we're going to look at solving trig equations, and I'm going to talk about 3 common errors that you'll see both in this little session and the ones afterwards. Almost everything has a second solution in 0 to 360. The only things that don't are at the top and the bottom of a sine curve, when sine equals 1 or minus 1, or cos equals 1 or minus 1. Apart from those, everything else is going to have a second solution in 0 to 360. And how we find it, we'll talk about in a moment. Another error is if the equation's got sine squared, cos squared, tan squared in, and when we square root it, forgetting to do plus or minus. So if it was sine squared is a quarter, for example, you need to do sine theta is root of a quarter plus or minus a half, and each one of those it was going to give 2 solutions in 0 to 360. And the third one, I'll talk about it in, not in trig form, but in another form, is when you cancel a common trig factor, you lose a set of solutions. And what I mean is this: if I'm solving 5x minus 10 is 0, well, I can solve it, I can move the 10 across and divide by 5 to get x equals 2. What I should be doing in reality, we tend not to do it, is this. And the only way that that times that can equal 0 is if x minus 2 is nothing, x equals 2. Because 5 can't equal 0. But when it's x squared minus 3x, for example, is 0, then in that case, if I cancelled my common factor of x, I would end up with x minus 3 is nothing, x equals 3. But what I'm losing is a solution set because I've cancelled the x out. Because x is 0 makes this true as well. What I should have done is factorised it, and then in each case that leads to x is 0 and that one leads to x is 3. By just cancelling the common factor out, I would lose x is 0 as a solution. In the sense the way if I was cancelling a common trig factor, I'd be losing sine x is 0, cos x is 0, tan x is 0 as a solution set. But we'll look at that basically in the second of these videos, not today. We're going to use what I call a unit circle to help us with solving equations and get an idea. So this is a circle of radius 1, that's what we call a unit circle. There's a point P, x, y on the edge of the circle. Now what it means is this: cos theta is x over 1, so x will equal cos theta. And similarly the height, y, there, will equal sine theta. Sine is opposite over hypotenuse. If the hypotenuse is equal to 1, y is sine theta. So for example, if I'm going to solve cos theta is 4/5, my calculator will give me one answer and one answer only. So I get my calculator, I press my buttons, shift cos 4/5, so shift cos 4 divided by 5 equals 36, rounds up to 36.9. Okay, now there is another place where cos will also have the same value, because what this is where we have the same x value. There's another point on this circle that has exactly the same x value. So if I sketch a circle like that and says this point here is where cos of it is 4/5, and so by by symmetry is down there. So that angle there is 36.9. That angle there is also 36.9 downwards. So one other answer would be minus 36.9, but that's not in our range. If I measure, and all our angles are measured, I've never really understood why, but it is, anti-clockwise from the x-axis. So the angle that goes from the x-axis to the one going downwards, that also has the same x value of plus 4/5, is actually going to be 360 minus 36.9. So 360 minus the answer, and that's 323.1. That also has exactly the same value. And in fact, how we get our second answer for cos is that they both will always add up to 360. So our method for finding our second answer is this. It doesn't matter if it's inverse cos of a plus or inverse cos of a minus. The two things are always going to add up to 360. Let's have a look at a couple of other ones then. I've got an example I'm nicking from elsewhere. It says tan theta is tan 42, and we've got a slightly extended range here from minus 360 to 360. So obviously theta 42 is one of them. I could have told you that. Tan does this. Tan is actually the gradient, because it's y over x is the gradient of the line. If changing y over changing x is the gradient of a straight line. So in this case, for example, if I did an angle of 42 degrees there, well, that's the same line. So that angle there of 42 will have the same y over x as going downwards like that. And because they're opposite, then all I do is do 180 plus 42, 222 degrees. If I wanted to go the other way around, to extend it beyond that or go further on, I keep adding 180s on, which would give me 402 outside my range, or taking 180s off. So if I did 180, feeling lazy today, minus 42, is that, I'll do it again, sorry, 42 minus 180 even. So minus 138 is another answer, and then minus 180 again from that, to give me minus 318 there. They are all in this range here, so I've got 1, 2, 3, 4 solutions in that extended range. Sine though, so tan, I'll sum it up, repeats every 180 degrees. And I'll use a little thing at the bottom here, because this is true for all of them. Everything will also repeat every 360 degrees, because we go around the circle. If I can imagine here, my unit circle, what would it end up doing to get exactly the same value of sine, cos or tan as that angle there? Well, if I've gone a full circle and then that extra, it's still exactly the same sine, cos or tan, because I've gone round a full circle plus the same bit again. So let's look at the two sine ones, because sine's a bit awkward. First things first, solve it. Sine theta is 3 over 4. So I'll get my calculator, shift sine 3 divided by 4, close bracket, equals 48.6 degrees. Now, what happens with sine, as we said before, that y was equal to sine theta. So if I do a sketch like this, if I have that point there, the place with the same y value is over here, like this. So whatever value that is, my theta, is the same going backwards like that. So how do I get the second answer? Well, it's going to be 180 minus 48.6 degrees. So 180 minus my answer, 131.4. So in this case, if it's sine of a plus value, because it can be different when it's minus, minus gives you a totally different answer, then they add up to 180 degrees. They are symmetrical about the 90. I'm going to have an acute angle and obtuse one. They're going to be symmetrical about the 90 degrees. In this case though, solve it. Sine theta is minus 4/5. Theta equals. I've got a problem here because I'm going to do shift sine minus 4/5. My calculator gives me an answer, minus 53.1 degrees. That's not even in the range. So I'm struggling already because what it's actually given me is this idea here. It's telling me that I'm down there at a minus angle because I've gone around the other way. So because I know that everything repeats every 360 degrees, what I can do to get my first answer is add 360 onto it. So if I go 360 plus my answer there, it gives me 306.9. I'm actually going to leave a gap. You'll see why in a moment. So that angle there is the one over 270 to get that thing. The other point on this circle with the same y value is down that way. I can either do 180 plus 53.1 or realise that they're both symmetrical about 270. So sine of a minus adds up to 540. So what I now know this one's 306.9, I can do 540 minus that answer, and that's 233.1. And that's my two solutions in the given range. My calculator gave me one answer, not even in the range. I need to add 360 to get a second one, and then in this case, sine of a minus, the two answers add up to 540. They are symmetrical about 270 degrees. Yet again, the other way we can look at it is to consider the sine curve and see how it's different from 0 to 180 and then 180 to 360 here. So if I'm trying to find where it's minus 4/5, the idea is I've got this point here and that point there. They are both at 53.1 degrees back from 360 and on from 180, but they both end up being symmetrical about that 270 there. Okay, so it's different for 0 to 180 than it is for 180 to 360. We'll look next time round at a few more solving equations and looking at the other examples where it all goes a little bit pear-shaped.